what I'm going to do to start is I'm just going to list out any of the things we've measured, any of the variables we've talked about since the beginning of the year. So at the most basic level, from the beginning of the year, what were some of the things that you measured?
Velocity.
Okay, velocity. Displacement. Time. What else? What do we start calculating from there? Variables. I want variables. Acceleration, okay? What was next? Force. Okay, after we covered forces.
Energy.
Energy. All right, so we had energy, and we had a few different types. We had kinetic energy. We also had types of potential. Okay. After energy, what did we talk?
Momentum.
Okay, we had momentum. We skipped one in there. Work and all right. All right. So there's a list of everything we have talked about so far this year. Okay. In terms of variables and properties we can measure. So if those are our linear values, then we're just going to take a look at this way. The first thing we're going to end up talking about is angular displacement. The second thing we're going to talk, well, time is just kind of time. Time doesn't spin. Oh, good. It can bend, but it can't spin. All right, next one, velocity. We're going to talk angular velocity. Acceleration, we're going to talk angular acceleration and centripetal acceleration. Force, we're going to talk torque. Kinetic, we're going to talk rotational kinetic energy. Momentum, we're going to talk angular momentum. And fortunately, work and power don't change. Okay. So these are the topics we're going to be looking at for the next few weeks. And one of the things you're going to notice is if you can handle linear concepts, you can handle the rotational concepts. Mathematically, they look almost identical. So as we're going through them, I want you to draw analogies between the rotational and the linear versions and use some of this rotational concept to help yourself review some of the linear stuff we've talked about in the past. Right. So the first topic we've got, as listed above, is rotational motion. And we're just going to start out by defining some of the key concepts to rotational motion. So first of all, everything we're going to be talking about is going in a circle. It can be going in a circle either as it's spinning about an interior axis or as it's going around in circular motion. So rotational motion occurs when something spins on an interior axis. Occurs when something spins on an interior axis, as opposed to circular motion, when something orbits or rotates around an exterior axis. Something rotates or orbits around an exterior axis. Okay. So if I've got, just say, a disk, and I've got that disk spinning, okay? Disk is going to be spinning, let's say, in that direction. First of all, I can start talking about, well, how far has it gone in terms of how many times has it turned, angular displacement. I can talk about how fast it's spinning, angular velocity. I can talk about if it's speeding up or slowing down, angular acceleration. Okay, so first of all, we can say how far is it rotating? That would be angular displacement. How far has an object rotated? Now, because we can talk about either rotational motion or circular motion in terms of these, I am going to just say rotated, but that could also mean orbited. That could also mean, no, that's basically it. It could be about its interior axis, or it could be talking about around an exterior axis. To illustrate that, let's say instead of just a disk, we place a ball on that disk, and we allow the ball to go around. So while the ball on the disk is going through circular motion and the disk is going through rotational motion, they would both go through an angular displacement. So I'm going to use rotates as referencing either of these two possibilities. Good with that idea? Okay. When talking angular displacement, typically we're going to measure that in radians. Measured in radians or degrees. And it's simply a change in orientation of a rotating object. A change in orientation. So displacement, talked about that. Time doesn't spin, so we can go on to the next one. Velocity, angular velocity. What was the definition of linear velocity? Distance traveled over a given change in time. Okay, in a specific direction. Okay. I believe we also said a change in displacement over a change in time, which, including both of your guys' definitions, would be basically the same thing. Okay. So angular velocity is going to follow a parallel definition. So instead of a change in displacement over time, a change in angle over time. A change in angle over time. Mathematically stated, so you guys are used to theta to represent an angle, right? Like that's something you've been doing in math for a while. Well, we're going to start using omega to represent angular velocity. That's lowercase omega for those who know the Greek alphabet. It's omega, clearly. Omega is angular velocity. You guys are really going to love the next one then. And we're going to measure this in radians per second. Alternatively, what units can I use for angular velocity? I could use, well, this is radians per second, but I could say rotations per second. Or RPM. For people who don't know what RPM is, that's rotation per minute. Okay, I was going to go for degrees per second, but all right, radians per second, rotations per minute. Any of these are good. Radians per second is the SI version, but we will encounter these other ones, and you'll need to be able to convert to and from them. Recognizing that one rotation is 2 pi radians. Good with that idea? I mean, it's one circle. Okay? All right. Mathematically, angular velocity omega is a change in angle over a change in time. Okay? And if I do a little bit of substitution, and I say that therefore omega must be equal to a change in pi r divided by time, and I divide both sides by r, I find omega over r is equal to change in pi over time. Well, that doesn't make any sense. Change in pi? Pi doesn't change. Well, one of the things we need to remember is that pi is a conversion factor, right? The other way I could have stated this is that it's the linear velocity or linear displacement over change in time. So when we are working with the linear values, I can actually work through it the same way. So if theta over r was going to be equal to pi, which was my angular, words are gone today. Pi r was my linear displacement. Omega r is going to end up being my linear velocity. Bleh, 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 bleh. Okay. All right. Next idea. Acceleration. Now there are two of them here. I'm only going to focus on angular acceleration today. We're going to save centripetal acceleration for a different day. Angular acceleration. What is the definition of linear acceleration? Change in velocity over change in time. Well, angular velocity is going to parallel that again. And this time we're going to have a change in angular velocity over a change in time. In angular velocity over time. Angular acceleration is the Greek letter alpha, lowercase, Greek letter alpha. What is it, Edmund? Oh, it's the Greek letter alpha, really, is equal to change in angular velocity over change in time. Yeah, and half the class is going to refer to it as fish.
But as long as you know what it is.
All right. So, given that this is change in angular velocity over change in time, units for this, guys, are going to be radians per second squared. Note the same format of the units as linear acceleration. Okay? And talking about a relationship between the angular version and the linear version, if we take alpha times the radius of whatever we're spinning around or traveling around, that's going to be our linear acceleration. Double add is when we're talking about pi r being our linear displacement, this was for our specific situation that we were talking about with the wheel. So if we wanted to find the linear displacement, we said it was pi r because we went half a circle, right? Well, what if we had gone a quarter of a circle? How far would I have gone? Say again? Pi over 2 times r. So theta times r is our linear displacement. So there is something that's not quite right here, and that's that this should not be equal to theta. So I did botch something up, sorry. So for our specific situation, it was pi r, which is the same as saying theta times radius is equal to our linear displacement. Okay? Is linear displacement, which the specific example of pi times r, say again? In radians, yes. All right, good with these ideas. So we've introduced 3 new variables, but all of them are just analogies for linear variables. And you can find the linear variable that they represent simply by multiplying them by radius. So alternatively, we could take any of these ideas, any of these new variables, and let me rephrase that. If we could take any of the linear variables and divide them by the radius of an object, we would wind up with the angular variables, correct? Okay, so we're going to do that. We're going to take something that expands upon the linear variables in a little bit more complex manner, and we're going to see what would occur if we divided all those values by r. So let's start with VF equals VI plus AT. Easy one, right?
Okay, that's good.
Let's divide everything by r. Take a moment, go through the algebra to divide everything by r, and substitute it for the variable we just defined. Yeah, it is. Perfect. Okay. So we can calculate different values for rotational motion based on something that looks almost identical to a linear kinematic that we've been using. Okay. Everybody pick another one of the kinematics, any of the other 3, and try the same thing. Try dividing the entire equation by r and see what you get. Coming up with? Who feels like they got one of the other ones? Yeah, Carter, which one did you do? Give it a shot anyway. Squared plus 2AD. What did you change it to?
Omega final squared equal to omega initial squared plus 2 alpha theta.
Looks good to me. 2 alpha theta. There we go. So to get that one right, you actually had to divide every individual term by r. So you had to separate out v times v and divide each v by r. Okay? Who's got another one for me? Was VIT plus 1/2 AT squared. What'd you get?
Theta equals omega initial times time plus half alpha times time squared.
And who got the last one? What is the last one? There we go.
Equals C equals 5 velocity plus initial velocity over 2 times time.
All right, so for this last one, all we add is theta equals omega I plus omega F over 2 times T. All right, so just looking at them, these should look familiar. These should, rotational kinematics should appear to be something you should be able to use because you've actually done this before. All we've really done is swap the English letters, the linear letters, for the Greek letters, the rotational letters. That's all that we've done. So let's take a look at how that would actually play out in terms of an example. So let's take a bike tire. That pops loose during a wreck. Rolls away at, let's say, 5 meters per second. Okay. if it rotates 22 times before falling down, what was its angular acceleration? What was its angular acceleration? Two things we're going to need to know. One, radius of the wheel. Radius of the wheel is 0.5 meter. And the other thing we're going to need to know is it falls over when it stops rotating. Okay. So I'm going to approach this in the same way that I would approach linear kinematics. So instead of listing VI, VF, ADT, I'm going to list omega I, omega F, alpha, theta, time. What do I know? I know theta. How much? How much? So I'm going to go with 22 rotations. And a couple of people have already converted it by taking 22 rotations times 2 pi radians to 1 rotation to get 44 pi. 44 pi radians. Okay? What else do I know here? Initial, how much? Well, this is omega I. I know VI is 5. How'd you get 2.5? All right, so just going to double check here because I'm out of practice. Angular velocity times the radius is my linear velocity. So I want to divide the linear velocity by my radius. And I'm not going to get 2.5. I'm going to get 10. Yeah, 5 over 0.5. 10 radians per second. Do I know anything else? There was one that I said. VF. Omega F. Because we said that the wheel was going to fall over when it stopped spinning.
What's this WI?
Omega initial. How fast it's spinning at the beginning.
Yeah, what is it?
10?
10?
Yeah.
What's the...
Radians per second.
Okay.
All right. Take a moment. Find the angular acceleration. All right, so looking at this one, if we wanted to find the angular acceleration, we probably should have chosen omega F equals omega I plus 2, wait, no, I missed the squareds, thank you, alpha theta. I've got 0 here equals 10 squared plus 2 alpha times 44 pi. And solve for alpha, I've got, let's see here, 100, subtract 100, negative 50 over 44 pi equals alpha. So whatever that is. It's like, what, 1/3 of a rotation per second squared? Negative how much? But I divided by 2. Negative point how much? 6.2. And that should be radians, not rotations. Radians per second squared. Now, fortunately, since you didn't use a trig function at any point in this, what mode your calculator was in doesn't matter. Okay? Because you didn't use a trig function, it didn't matter that you were in degrees. That it was coming to a stop, that was 0. Omega I was 10. Alpha, we didn't know. Theta was 44 pi. Plugged them in. 10 squared is 100. I subtracted 100, and then I divided by 2. I got negative 50 on this side. Then I divided by 44 pi. Negative 50 over 44 pi equals alpha. Abby punched it into her calculator and got that value. Yeah, Carter.
I got this place on the off, get 3.5 trim routing, I'm sure.
Yeah, that's probably one of the biggest mistakes we see is parentheses. All right. So, let's try one more.